There are two main types of questions you run into when it comes to power. The first type is when you can easily work out the work being done by something. So by a person dragging something or a machine lifting something, and you're also given the time. And from that work you can work out, that work you can solve, and the time, you can find the power. The second type of question is when you have, it's usually a car moving at a certain velocity. And you know that you can figure out the force that the engine is applying to the car. From that you can work out the power. And that requires some kind of, no, it actually doesn't require a constant velocity, but it does require you to work out the force of the engine, which is usually equal to the resistive force. I've yet to see a question with acceleration. We'll cover that in a second. First of all, let's do this find the work and then use the time to find the power type question. Say we have a fridge, which is already sitting on a shelf at a height of 1 meter. And then we move it up to a shelf at a height of 4 meters. So there's the fridge in the first instance. We'll say that's the ground. 1 meter, 4 meters. And that fridge can have mass 90 kilograms. And the time taken to raise this fridge at a constant speed is equal to 8 seconds. Let's figure out how much power went into raising the fridge up to that higher height. Now, using your common sense for a second, if you went to the gym and you saw someone with a very heavy weight, a very heavy dumbbell, and they lifted it into the air very quickly, you'd say that person must have used a lot of power. They must have had very powerful muscles. That's because the time taken to lift it went down, therefore the power went up. Likewise, if you saw someone with a very heavy weight lifting it into the air, you'd say, well, heavy weights have a lot more gravitational potential energy up here than light weights, so the work done must have been great, and if they did it quickly, that means the time was also small, and they must have had very powerful muscles. So when heavy things get lifted up quickly, that's a lot of power, and when light things get lifted up slowly, that's little power. So let's think about this fridge. In order to lift it up that 3 meters there, so that's 3 meters of, no, sorry, it's more like this. The 3 meters was equal to the change in height. And the change in gravitational potential energy is equal to mg, change in height. So that's 90 times g is equal to 10 in year 12 physics, so 10 times 3, which is equal to 900 times 3, 2,700 joules. So the fridge up here has 2,700 more joules worth of gravitational potential energy down here. In order to have given it this increase in gravitational potential energy, we must have done that amount of work to it. So the work done to lift this fridge up from 1 meter to 3 meters, 1 meter to 4 meters, which is a change in 3 meters, is 2,700. So this is the first type of question where we figured out the work, and now we use the time to figure out the power. So the power is equal to the work over the time. That's 2,700 divided by 8. And I have that coming to 42.2 watts, because power is in joules per second, and that's another way of writing watts, big W. Let's check that answer. 2,700 divided by 8. No, it wasn't 42.2. That is a calculation error by myself there. 2,700 divided by 8 is equal to 337.5. 337.5 times 8. Yeah, that's right. Don't know what happened there. I must have changed a figure around in my working on the paper here. So since we knew the work and we knew the time, we figured out the power. 337.5 joules per second, or watts. And what that's saying is for every second that passed, 337.5 joules worth of work was done. Let's look now at the second type of question, involving a man dragging a barrel through the desert. So we have the barrel, desert sand, barrel here. Now it'd be easier for him to roll the barrel, but rolling friction gets a little bit difficult. So there we go. And the information we're going to give is that he's moving at a constant speed of 0.6 meters per second. And in actual fact, this doesn't have to be constant. We'll just say an instantaneous speed of 0.6 meters per second, and that's the positive direction that way. So he's moving clearly that way. The barrel, we don't need to know its weight, but we do need to know that there is a resistive force, resistive force this way, of 100 newtons. And actually we will say that is the constant speed, so constant speed. From just this information, we should be able to work out the power of the man on the barrel. If he is moving at 0.6 meters per second constant speed, that implies that the acceleration is equal to 0, which implies that the sum of forces is also equal to 0, because the net force is equal to the mass times acceleration. If the sum of forces is equal to 0, that means the 100 newtons in this direction must be matched by 100 newtons of driving force in that direction there. So the driving force of the man is 100 newtons. And if we go straight to our formula now, power is equal to the force times the velocity. We get power equals 100 times 0.6, 60 watts. Let's analyze for a second why this formula actually works. So let's look at an instant in time, t equals 0, and then we'll look at another instant in time, t equals 1, when the barrel is now over here. By the time the barrel moves from here to here, the work done by friction is equal to negative 100 times that displacement there. What is that displacement? Well, if he's moving at 0.6 meters per second, and this takes place over 1 second, the displacement is equal to 0.6. That's negative 100 times 0.6, or negative 60 joules. If this is the work done by friction, and this barrel and the man are not accelerating, so it's constant speed, that means that this must also be the work between this point and this point, which the man put into the barrel. So that's the work of friction, and this is the work of the man on the barrel. So that also equals 60 joules. And we already said the time taken to go from here to here was 1 second, so we can use the formula power equals work on time, that's 60 on 1, or 60 watts, 60 joules on 1 second, 60 watts. So since we can look at the snapshot 1 second later, and then we can actually find out the work, we can use that 1 second, which is arbitrary, to find the power. Here's another way of putting it. Power is equal to work on time, which is equal to force times distance on time, which is equal to force times distance on time, we can move that t just under the d, which is equal to force times, what is distance on time? Well, d equals vt, distance equals velocity times time. Actually, we'll say speed. Distance equals speed times time. So distance over time is equal to velocity. So power equals force times velocity. I think memorizing these two formulae is the way to go.